First of all, I'd like to thank the organizers, Professor Suo and Prof. San, for inviting me to this wonderful conference. And I'd like to thank the other people in KAIST for arranging a lot of things for the conference participants. Thank you very much. Today I will talk about Schubert calculus, which studies geometry of homogeneous spaces, especially the cohomology ring of Bragg varieties. In the first hour, I will briefly discuss what is Schubert calculus by considering the most fundamental case of Grassmannian, which is homogeneous, can be considered as homogeneous space. And here we don't consider torus action. And the second hour, I will consider the general Bragg variety, and I also consider torus action on it. So let me start with a quiz, which was first posed by Hermann Schubert. So this explains why we call Schubert calculus. So a kind of answer for this line. Problem goes as follows. How many lines are there in Euclidean free space, which means all the four lines are for the four given line. Please take time to consider this problem yourself as a morning warm-up.
When was it given?
When? First we have four lines.
No, when? Which year?
When did he give this kid?
Schubert, when?
More than 100 years ago. So he was born just 20 years after famous Franz Schubert, famous composer Franz Schubert died.
Oh, died.
Yes. So this is before in 19th century.
Is it relative of the composer Schubert?
No. So as far as I know, everyone asks such kind of questions. So how can we solve? First, we divide the four given line into two parts, and move continuously those two pairs, so that each pair has an intersection. Then we can draw the solution like this. First solution is how the line goes through these intersection points, and we can draw one more as which arises as the intersection of two planes spanned by each pairs. if you have two planes in R3, then which intersects by the one-dimensional line. So that one is, and that's all. So but the crucial point is we have to assume that the number of solutions won't change if we rearrange the initial lines.
So indeed, 4 lines are on the same plane, or?
No. So first the 4, yes, that's for given lines in general position.
How the second line?
Okay, second line appears as, for example, yes, intersection of
So what do you mean by arrange two lines meet together? This is not the given original line.
Yes. So we have to
change it.
Yes, we have to assume that the number won't change if we rearrange some continuously and regularly. We move. So what is regularly? So that is a problem. But intuitionally, the number of solutions don't change if we don't move. Like for example, if we rearrange those 4 lines so that the 4 lines are on the same plane, then the number of solutions change. But if we move carefully or avoid some singular point, then the solution won't change. So, but this argument is not so rigorous. And Schubert formalizes this kind of argument, but Schubert's argument is still not rigorous, but can be formalized as follows. We consider the following conditions on a line and denote them by some symbol. A line is, the first condition is a line is intersecting a given line. Second one is given point. Line is passing through a given point. And the third one is on even plane. I forgot the spelling. No. N-E. And by this symbol, we mean given point. And given line. So final one means a line is just the same line as a given line. Then, using this formalized symbol, we can do some calculus regarding this kind of argument. So, the solution the first problem can be considered as the condition. A given intersecting a given line and given line and given line. So this means a line is intersecting the all the four given line. This symbol means and. So how to calculate this condition? So for example, this means a line is intersecting a given line and another given line. So it is equivalent to this one. Since if we are given two lines, then here we have to move the two lines to meet at some point. Then we can translate this condition as a line must go through the intersection point, or a line is lying on the plane spanned by the two lines. So we have this calculation. And just similarly, we have this formula. So this becomes
this is associative.
yes, because this is logic computation. logic is associative, and logic is distributive. We can distribute use with distribute rule here. So here we get the answer, because this means a line is a given line is equal to a given line. So a line is equal to some given line, or a line is given to equal to some given line. So it means there are exactly two lines satisfying this condition.
Could you explain please the second one?
Second one, this one.
Yeah, so why does it on a given line and intersects a given line is equivalent to...
Okay.
The first I understand.
On a given plane and intersecting a given line.
The
It
plane is
means
divided
yes.
by two lines.
Yes.
Yeah.
Could you explain the first one?
First one.
Yes, it's a tail. No.
This
one.
This-
Yeah.
This one. This one. So first we have to move two lines to meet.
We can move,
at-
right?
Yes. So this part is not rigorous. So to give a rigorous foundation for this Schubert's argument was a problem by Schubert. And that was major subject in the first half of 20th century, and now it is solved. As intersection theory. This is equivalent to just homology theory of resonance.
What was Schubert 15th problem? It's difficult.
But was okay. So there are two kinds, or there are two problems in Hilbert's 15th problem. The first one is give a rigorous foundation for the argument of Schubert. And second one is give an efficient algorithm to calculate these kind of. Now first one is solved, but second one remains open. So which we call Schubert calculus nowadays. The original problem is now restated in the setting of homology theory of Grassmannian, like this. 2, 3, 4. Grassmannian of two planes in C4 is defined as dimension 2, complex dimension 2. Linear subspace in V4. and each condition for a line corresponds to some subvariety, submanifold, closed submanifold in Grassmannian. So it mentioned time. So what is the volume for lambda? It's just the number of boxes here. Just anyway, the condition for a line corresponds to some submanifold. Just this correspondence can be seen just intuitively because a line in our okay. So we have to projectify everything. A line is a plane in projective settings. So these conditions can be restated as conditions for a plane in C4. Then it corresponds to some manifold in Grassmann. And we can consider this submanifold as the homology class of Grassmann. And it is known that one and these classes forms the Z basis of the homology. So we can write cup product of two homology classes as a linear sum of other these classes. Because they forms Z basis. So problem is find an R O V Z for this constant, and this constant is called structure constant.
Excuse me, I'm wondering if the lines are real, right, in real space, but here you have complex Grassmannian.
Yes.
Is it like because intersection theory is simpler, or why do you not consider
yes.
real Grassmannian?
Because we have to consider algebraic setting. We need so yes for the intersection theory. But the first problem, the original problem, the number of solutions doesn't change if we tensor by C, because the which is given just a system of linear equations. And this problem,
So in other words, the Schubert calculus for complex variety and case and real case, it's same or?
No.
No,
For
it's not. The original problem is.
yes, if we change here by then we can also consider this kind of problem, but only in Z2 coefficient, because there is many two torsion. And so this is the problem, main problem of Schubert calculus. And this structure constant have a lot of meaning in other areas. For example, first one is obvious. So ring structure for lasagna. So this is a problem in algebraic topology, and the second one is second one is just the motivation of Schubert, counting some number. The third one is tensor multiplicity. For irreducible representation of symmetric group. As you can see, the index for this subvariety, I used some boxes. That one is actually Young diagram, and Young diagram is 1-to-1. Young diagram corresponds 1-to-1 to reducible representation of symmetric group, and this gives a tensor multiplicity for the decomposition of two irreducible representation. And the fourth one is from combinatorics. Shear function is a series of symmetric function, and it forms a basis for the ring of symmetric functions. And the problem here is if you multiply two shear functions, or if you are given some symmetric function, then can you give decomposition the given symmetric function to shear functions? So this structure constant solves also this problem. How to approach structure constant? So there are many approaches, but since I'm algebraic topologist, I prefer to use algebraic topology. And some combinatorics. So how?
What is the other approach?
For example, for the case of Grassmannian, we can write this submanifold explicitly by using matrix, because Grassmannian elements corresponds to matrix. Then we can carefully look at how they intersect. Then you can obtain structure concept. So how we can use algebraic approach and combinatorics? Fact. The cohomology of Grassmannian is known to be quotient ring of polynomial ring with many variables. Okay, since I don't have much time, I omit the relation. We can so this generator has dimension 2 and can be considered as first Chern class of line bundle, which appears as the decomposition of tautological bundle over Grassmannian. So question one is find a polynomial representative for this submanifold. This submanifold is called Schubert variety. So to find a polynomial representative for Schubert variety, because we can write cohomology class as a polynomial. The second problem is we have to know how to deal with ideal calculation. More explicitly, if we have some polynomial here, can we have some efficient algorithm to decompose this one into Schubert basis? Find your polynomial representative.
In that presentation, do you mean xi is of degree 2 or degree 2i?
Degree 2.
xi.
The general.
Degree of xi.
2. Because yes, we have another presentation for Grassmannian using just Chern classes, but we consider as separated. So first decompose the tautological boundary by line bundles by bring back to black bundle, and then we consider there. Because we want to keep some symmetry. So if we solve Q2, these problems, then we have the answer for structure constant.
Can you explain one more interest argument?
Here? Oh, okay. So we have a tautological bundle over Grassmannian. Then we can pull it back to some manifold. Then we have splitting principle.
How it defines FL?
FL construction.
How it defines?
FL is the construction is, for example, if we define Grassmannian as a homogeneous space sharing C by some P, then Flag variety corresponds G, F, and C divided by B. This is projection. But if you don't, so you don't need to this explicit construction.
There is some manifold
yes,
where
yes.
you can
Split.
You can pull back and then you bundle.
And this xi can, is identified with C1 first chunk class for Li. N plus 1.
M plus N, right?
M plus N. Yes. Yeah, N, sorry. N plus 4. Yes. Yes.
But still, it just embeds right into that polynomial ring. That
Yes,
cohomology
yes.
of Grassmannian embeds into the cohomology
Yes.
of the Flag manifold symmetrical. But I mean, you're right that it's isomorphic to the quotient of the polynomial ring on even-dimensional generators.
Yes.
I agree that it embeds into polynomial rings on even-dimensional generators, modulo something. But why this? This I understand that the cohomology of the Flag manifold is okay. It is like that.
Yes.
But the cohomology of the Grassmannian is a subring there, right?
Yes.
So
No. So homology of Flag variety
yeah, it is.
polynomial
Yeah,
divided by
Yeah,
so
yeah, that's
invariant.
I agree. So it's of that form, right?
Yes.
But then you embed the cohomology of the Grassmannian, right?
Yes.
And so it's. But here you wrote that. So for example, for the two-dimensional. Okay, well maybe I'll better ask it later because.
Sorry.
But here, then, see, okay, I, the number of I is N, right? Now that
Yes. So I have to
the equation is only the N number of
N plus M. N plus M.
C and Li, right? The number of Li is just N, right? N or M, not N
Yes.
plus M.
Yes. N or M.
Here,
Yes.
You use N plus M, right?
Okay. So how these appear? So we need so we also consider this band, and the relation here is this sum up to trivial. Okay. In fact, the solution for both questions are known in the case of Grassmannian. But so the problem of Schubert calculus is for the other cases. But instead of describing the solution for Q1, Q2 for Grassmannian here, I will show some similar problem in more familiar setting of Bott tower. So, I think everyone here is very familiar with Fukuoka, so I just briefly write the definition. A bot tower is a sequence of CP1 bundle and the first stage is just over point. And each stage must be written as a projectivization of some two line bundles. So we have a canonical section by sending base points in the base to the infinite in the Python. And the cohomology of bot tower is known to be a polynomial ring divided by ideal xj is less than I. Okay. Here is the
is linear.
Yes. The Euler class for the each stage. So EI can be written as minus AJI x JXI or some linear also or some matrix AJI. We can define submanifolds of gamma as follows. For each lambda in
xj or
sorry.
xi or xj?
EI is AJI.
What is this? You have j is value, right? So
Yes.
j,
J.
You should remove the sigma and you should replace J and I.
J. Yes. Okay.
right? Yeah.
This is correct. Thank you. Sorry. Okay. So for each lambda in the power of 0, 1, we can define some manifold gamma lambda as the image for I need a lot of notations for inverse Sn minus we should write not inverse of point. And a closure. What this means, if you have lambda I 1, lambda. So whenever you have 1 in this, some i's position, then you take pi inverse there. Whenever you have 0 in the sequence, you take this. So this is not so difficult. This means if you, so whenever you have 1, then you can fiber. you can have fiber here.
Which one is the example? Which is the example of the lambda?
Okay. So for example, if we write lambda for like this, one line notation, then lambda is I inverse 3. Yes. So I inverse 3 is 2 I 1 inverse point. So CP1, CP1 bundle over CP1. Then it's easy to see that this gives cell decomposition for Bott tower. So the cohomology of Bott tower is just a free Z module generated by gammas. And also we know the cohomology class of this one is identified with x number. X lambda means, for example, x lambda is x3, x1. This setting is very similar to Schubert calculus. We know the we have polynomial representation for the cohomology and also the basis for the cohomology. And this means we have a solution for Q1. What is Q1? Find a polynomial representative for each basis. Actually, in the case of Bott tower, we can solve the second, we can give it the answer to the second question also. So how? Because the structure given by polynomial representation of the cohomology is very easy.
What is this notation? Z gamma?
3 gamma.
That's a
So this means the gamma. Okay, the gamma. So which means gamma lambda forms the z basis for the total.
as a group they are there.
Yes, just as a yes, Z module. So what is the solution for question 2? For the question 2, I just give illustrative example. Because that giving a matrix determines the structure or sequence of CP1 vibration. So determines the cohomology of hot power. And so here we consider this equation. So the second statement says that this is equal to x4 plus x1. And we can this is the right. Okay. Anyway.
Yeah, explicitly right.
Yes. Using the relation. Yes, x. For example, x4 square is just x minus 2 times x1 x4 plus x2 x4 plus x3 x4. So using this kind of relation, we can explicitly compute to have 1 x2 x3 x4. And this is mysteriously corresponding to the solution for the first problem, but I have no time to explain this correspondence. But, anyway, because we have a good form of EDR, we can calculate. This type of EDR is very easy to handle, since we have some ordering, and if we apply this translation, then we always get lower term in reverse lexicographical order. But between these omitted dots, we have many cancellation. What is cancellation? For example, just before this line, we have this kind of cancellation between plus and minus sign. So what we want is preferably we don't want these cancellation, and this is also a problem for Schubert calculus. But okay, so I don't give a correspondence between this calculation and Schubert calculus, but just give some open problem for Bott tower. Bott summation variety. So what is this? Bott summation variety for type A is certain Bott tower defined by an element of symmetric group. This is symmetric group. And put AJI as Cartan number for sorry, this notation I have to explain. Symmetric group can be written as the composition of simple transpositions. It's just W1 and plus 1 simple transposition. W is in 1 to n minus e 1. Given by the Cartan number of simple root, but we have an explicit Cartan number. Explicit description for the case of type A. This is zero if or if I is less than or equal to j, then the entry will become 0, or wj minus w I is greater than 1, then the entry is 0, and 1 if wj minus wi is 1, and I is j minus 2 if so the open problem is okay, I think I have to stop now and continue in the next.
Yeah.
Sorry. So anyway, this is definition. This finishes the definition for the Bott summation tower, because this number gives structure for Bott tower.
What is a part of the tower?
Part of, right?
Not all of the Bott tower.
Not all of the Bott tower can appear as like this, but yes, this defines a Bott tower.
Is there any question?